Thank you very much, Almok, for the introduction. So I'm going to be talking to you about black holes and how they explode things, okay? So no falling asleep yet, all right? So I'm going to talk more about what you've seen here, so keep awake for that. But before I go on, I wanted to give you kind of an introduction of what's happening in the field of black holes. Big black holes happen and small black holes happen. The big ones are the centers of galaxies. They weigh millions to billions of solar masses. And the small ones, they live in binary systems like X-ray binaries, where a normal star feeds a black hole, in compact binaries, where two neutron stars can merge and make a black hole, and that's a very important system. We see these in a variety of means. The first means by which we inferred the presence of these was a gamma ray burst that came out from the outflow that I don't show here. This is a jet that comes towards us and emits in X-ray. So these are seen as maybe 1 second longish flashes of gamma rays on the sky, or shorter. And these are core collapse gamma ray bursts when the star exhausts its fuel and is ready to die. Its core collapses, forms a black hole neutron star, which launches a pair of highly magnetized, we think, jets that once they get out of the star, they produce a flash in gamma rays that lasts minutes, perhaps. 100 seconds is a typical duration. So both of these are referred to as gamma ray bursts, short and long gamma ray burst. So far, this is pretty binary, big and small, but recently there is evidence for an intermediate class of black holes, not surprisingly named intermediate mass black holes, that bridge the gap between supermassive and stellar mass black holes. And these could be either a low mass and extension of heavy things or high mass extension of light things. So it could be heavy binary, or it could be perhaps a low mass supermassive black hole. And these are really interesting, guys, because given their, if these are intermediate mass black holes, they could be massive enough to power ultraluminous X-ray sources, which give off too much X-ray emission for their mass had they been stellar mass black holes. So this is a very active field with a lot of interesting things going on. But before I go there, I want to give credit to where it belongs. Black holes are not the only things that can produce these collimated outflows, about which I will be talking a lot today. Things with surfaces, such as neutron stars and white dwarfs, and normal stars can also produce jets. This is, by the way, the only real observation of a jet from in a planet-forming system, in a star-forming system. This is really exciting field with lots of developments. For instance, there was a discovery of gravitational waves just a few years ago, and I show this. I illustrate this with the picture of black square by Malevich. In fact, I will argue that he predicted gravitational waves because we didn't see anything. We only heard gravitational waves, so that's why black square is the illustration that I used. There are many other exciting discoveries. More recently, there was, of course, the detection of optical counterparts and gravitational waves from a merger of two neutron stars. Happened in August 17th, 2017. And this event, or these types of events, are really exciting because they allow you to probe the same system through different messengers, gravitational waves, and various different signatures across the electromagnetic spectrum, of which I'm going to tell much more about in the next half of the talk. There are other exciting discoveries, such as ultra-long duration gamma ray bursts that last, instead of minutes, they'll last hours. How can you have such a long duration gamma ray burst if it comes from a depth of a star? It better be really big. Also, not only do these things produce jets, they also apparently explode stars magnetically, because there was a signature of that in the light curve afterwards. There was a bump. So that means that if the explosion is you inflate a balloon with magnetic pressure, like you take a balloon and inflate it with air, it inflates. But here we have two holes, one for each jet. So you're inflating a balloon with the hole. And you need to fine-tune the rate at which you inflate the balloon such that it doesn't deflate. Otherwise, there will be no explosion. But also, you want the balloon to explode at the end and produce two powerful jets through the holes, which is weird. How does nature manage to fine-tune that? I'm not quite sure. So that's a question that I would be really happy to talk to you about if you have any ideas. Another dramatic discovery that happened relatively recently came from the observations of New Star satellite that detected pulsations from what we thought was a hyper-accreting neutron star, hyper-accreting black hole, or maybe supermassive black hole in intermediate mass range. It turned out to be a neutron star because we saw pulsations from the surface. So ultraluminous X-ray sources could be just 1.5 solar mass neutron stars, which is something that we're still processing. We're still trying to understand how come neutron stars can be so luminous. Is it always a neutron star that is powering an ultraluminous X-ray source, or are some neutrons, or are some ultraluminous X-ray sources powered perhaps by black holes, and are some of them intermediate mass black holes as opposed to stellar mass black holes? So an active area of research, a lot of excitement here. And finally, the last but not the least, we can light up supermassive black holes on our human lifetimes by feeding them stars. I know there is a lot of research here going on in this area. So if a star comes too close to the black hole for its tidal forces to rip the star apart, overcome the internal gravity forces keeping the star together, well, then the star loses its identity, becomes a long spaghetti. That spaghetti can form an accretion disk. And what's really exciting, it can also produce a pair of jets. It's an amazing system. It's a calorimeter of accretion and ejection, because we know pretty well what the mass of the star was, give or take a factor of 2 from 1 solar mass. And then if we know how much mass the black hole ate and what the power of the jets and the luminosity of the system that we detected, we could try and understand qualitatively, to within a factor of few, what is the radiative efficiency of accretion? What is the efficiency with which jets are produced? So I work on almost all of these aspects except for merging the black holes themselves. So if it's bright, if you can see it, myself and my group are working on that. So if you're interested about any of these systems, please come talk to me, follow up with an email. I would love to interact. But here I will focus on just a few of these aspects, given that I only have about 45 minutes left. So let me first motivate, before I go on deep into the woods and the details, why do we want to study black holes? And I will pick a supermassive black hole as a motivation. Well, because if we put a black hole in the middle of a galaxy, it explodes the galaxy. What is a black hole? It's essentially a magnet that spins. And if you put a magnet that spins into a galaxy, it will explode the galaxy. You put it in the middle of a star, it will explode a star. You pick your target. So here we see a supermassive black hole in the middle. This is X-ray emission in 3 colors. And if you do some image magic to it, if you sharpen the features, you will see a couple of bubbles which are inflated by the activity of the black hole, presumably by the jets. And these bubbles also produce trains of shocks or sound waves that presumably heat up the inner parts of the galaxies, a process that is pretty elusive, but the one that we need in order to avoid the cooling flow problem in galaxy clusters. There are many more examples, such as the M87 Galaxy, where you see more of the same, the shocks and the cavities inflated by the activity of the central object. And finally, my favorite example, the cluster of galaxies MS0735.6, where you see this huge, actually this is where I'm making my dramatic move, and I'm closing the window. Yes, you will see the colors much better now. So these purple regions are the regions that radiate radio emission in synchrotron. And you see where there is magenta, there is no blue, which is thermal emission by X-rays. And so you can see that literally this really relativistic plasma was inflated by the activity of presumably the black hole through the jets. And it actually did work on displacing the surrounding ambient thermal gas. And that work, if you compute it and compare it to the rotational energy of the black hole, presumably that's the energy reservoir you can tap, they are comparable to each other. So it means something came with a big stick, took the stick, it should be conducting, stuck the stick into the black hole, took away all the energy of rotation from the black hole, and dumped it into these big lobes. How that works, I'm going to try and tell you. But before I do, let's try and understand this process of coupling between the black hole and the surroundings, which is called black hole feedback, more quantitatively. This is one of the most popular ways of seeing that there's something going on in there where we plot along the vertical axis the mass of the central supermassive black hole, ranging from 1 million to a few billion. And along the horizontal axis, we're going to plot the central velocity dispersion in the galaxy bulge, ranging from 60 to 400 kilometers a second. And what we see here is that they're not random relative to each other. There is a tight correlation known as the M-sigma relationship. And you will tell me, what's the big deal? I mean, of course, the stars feel the gravitational potential of the black hole and they adjust. It turns out it's not quite that, because the black hole weighs only 0.1% of the galaxy bulge. Which means that these stars, they actually don't feel the gravitational pull of the black hole. They feel the gravitational pull of the stars, of the dark matter, and all the rest, all the good things that the galaxy is made up of. So how come the galaxy itself is aware of the black hole mass? That is the big question, because this black hole is a tiny little lot at the center that the stars don't know directly anything about. So how come the galaxy knows about the black hole? Is it because the black hole explodes it via jets, or is it because black hole blasts it with a radiation? These are open questions. It's also possible that there is no direct connection or crosstalk between the black hole and the galaxy. It's possible that both the black hole and the galaxy grow together at the same time by related processes, and that's why there is a correlation. So it's still up for grabs. Okay, that hasn't been so helpful, has it? Been for understanding black hole feedback. So let's try and look at pictures. Hopefully pictures will help us understand what's going on. And these are two of my favorite radio jets. They are radiated at other frequencies as well, but in radio they're particularly spectacular. This is Cygnus A Galaxy, and that is the M87 Galaxy that you already saw before. And here, if you look at these two images, you will see that even though the central black holes are about 10 billion solar masses each, this jet looks like it's straight and ends up with a hot spot, and this one is kind of fallen apart. Moreover, we're not even seeing the other jet here at all. What's going on? Well, what's going on here is a dichotomy that von Neuhofen really noted more than 40 years ago that classifies these sources and these sources as type 2 and type 1. Von Neuhofen really type 2 and von Neuhofen really type 1 sources. What causes this dichotomy is not clear. Is it the difference in the accretion regime? Is it difference in the ambient medium? Is it a combination of both? Is it the magnetic field that the black hole is fed? Different geometry? It's unclear. And so that doesn't help us much in understanding the black hole feedback. But if we were to zoom in even further, we will see that there is pattern moving away from the center. So these jets, they don't start out of nowhere. They start very, very close to the black hole event horizon. In fact, probably at the very event horizon. And as they move further out, they expand and they accelerate. And I will talk more about this. And so by the time they reach these scales of about 3,000 light years, so divide by 3, get the number of parsecs. So it's about kiloparsec scales. They already are moving at Lorentz factor that is large, at speeds that are very close to the speed of light. That's why, due to the relativistic Doppler boosting, you do not see the other jet. The other jet is boosted away from us. So the aliens on the other side of the black hole will see that jet, but not this one. But then once the jet starts interacting with the ambient medium and starts to heat the galaxy up, that's where it slows down and falls apart. This swoosh you're going to see on the other side because it's no longer relativistically moving. So this is a really rich system with a lot of interesting things, time delays, relativistic motion, Doppler boosting that's happening here. And in fact, we can more quantitatively measure how fast these jets move, because it's really important. How can a black hole produce this huge streak across the sky that moves at literally the speed of light? Oops, sorry. So here, for instance, is the image of the central part of M87 jet. And you can see that there are several exposures shown, starting from 1994 and all the way through 1998 every year. And you can see that you can connect different parts of the jet between different times. So there is a non-moving component, stationary component, that is presumably associated with the black hole. And then the other components are moving away. These are pieces of the jet that are individually emitting. And you can connect them with straight lines and measure what the slope is. And it tells you that the jet moves on the sky at an apparent speed that exceeds the speed of light by a good factor, factor 6 here. How can this be possible? Well, of course, nothing is moving literally faster than the speed of light. It's just an effect that comes from the fact that when the emitter moves close to the speed of the light itself, when it catches up with its own emission, it appears on the sky as if the emitter is moving faster than the speed of light. This is a signature of relativistic motion with Lorentz factors of order that number, of around 6. So that allows us to measure the speed of these jets just from the dynamics of these blobs on the sky. Not only that.
Well, you had the beautiful pictures. The most remarkable thing of these jets is how there's nothing that seems to be coming off the sides. There's no reverse shock structure in the radial lobes associated with the surrounding outflow. Are you going to be able to explain that?
Maybe, if I have the time. I will try at least. But if I don't get to that, I'm happy to talk after the talk. That's a great question. But another thing that's remarkable about this is not only how smooth, how close to the speed of light this jet can get. It's how smooth the way it approaches the speed of light is. I will not quite show that, but what I will show instead is how the width of the jet, which is this, the jet width, depends on the distance away from the central black hole. So this is 1 gravitational radius. This is 10, 100, 1,000. This is 100,000. And here it's 100 million. And you can see just between 100,000 and 1 million gravitational radii from the black hole, the shape of the jet shape switches from something that looks almost like a parabola, distance along the jet z, scales as this almost a square of the cross-sectional radius of the jet, r cylindrical, and then it becomes steeper. So it becomes it becomes linear. So how does it work? Oh, and why it's becoming steeper? It's because it's r versus z. So this dependence becoming steeper. Okay, I don't want to get into the geometry here. Ask me later if you have questions. So what we see from here is that the jet itself maintains for about 5.5 orders of magnitude almost continuous parabolic shape. How in the world is possible? What is it telling? What is telling the jet to be a single parabola? That is a mystery. And moreover, how does this parabola manage to accelerate the jet? So what are the questions that I'm going to address today? Well, first question is, what is the healthy jet diet? What do we need to feed the black hole with for it to produce a healthy jet? Second, what sets the jet power? I would like to understand, if I see a jet of a certain power, what does it tell me about the underlying system? Black hole mass, black hole spin, magnetic flux, the amount of mass that the black hole is being fed. So how does this how does this power relate to the accretion rate, for instance? What sets the Lorentz factor of the jet? Why do these jets accelerate? And what can we learn from the measurements of jet Lorentz factor? What sets the jet morphology? Why some jets look like they're falling apart, the other ones that look as straight as the laser beam without any signs of instability? And finally, we don't expect that all the systems look like disk in the equatorial plane, jet perpendicular straight out of it. There could be misalignment between the disk and the black hole. So, so what is setting the direction of the jet? When we look at the jet at a large distance, is it the black hole spin that's telling the jet where to go, or is it the disk spin direction that tells where the jet should go? These are all open questions, and I'm going to try to address them one by one. Before I do that, I wanted to give you a brief introduction on how these jets get launched and how they get accelerated. So I'm going to replace the central object with the perfectly conducting spinning sphere, and I'm going to replace the ambient medium that the jet has to drill through with a perfectly conducting ceiling. The ceiling doesn't spin, so don't worry about that. The magnetic field line by one end will be initially attached to the ceiling, and by the other end to the surface of the object. And I'm only considering one field line. There will be many other ones. I just pick one for illustration. So what will happen if we let the central object spin at an angular frequency omega that we keep constant, and we'll wait for n rotations? Well, we will get in the end n toroidal field loops, one loop per each rotation. And if there is toroidal field, there is toroidal pressure, b phi squared over 8 pi, which will be pushing on the ceiling. It's a magnetic spring that we have twisted here, right? From the bottom, and then the top will feel the push. So if we wait for longer and longer, more and more rotations will put more and more loops on this field line. B phi will go up, and the spring will be stronger, and eventually it will push the ceiling away, and it will expand under its own pressure. That's what these jets are. Literally, it's a continuously twisted magnetic spring from the bottom that tries to run away from the center where the pressure is higher as fast as it can, and eventually it can accelerate to near the speed of light. Okay, you're telling me that, I'm telling you, I mean, you're asking me, are you telling us, Sasha, that this is how it works? Can you show us that it indeed will happen this way, and why would this jet be having a shape of a parabola? Well, how do we answer hard questions? We turn to the help of bright graduate students, and a lot of this talk will be based on the research of really bright young people. So a perfect example of a great graduate student is Kaushik Chatterjee, who is going to be in the job market next year. So keep an eye out for him. He's amazing. So let me just show you how we can simulate these systems. So this is an accretion disk around the black hole. And these are the jets powered by magnetic fields. I will tell you more about how that works in just a moment. But let's take a look at what can the simulations tell us, because this is so far pretty close in, maybe 100 gravitational radii from the black hole. What can the simulations tell us about larger scales? Well, let's try and run the simulation and see what happens. So you can see that there are, of course, non-axisymmetric instabilities, and the jet is a bit wobbly. And now we start zooming out, and we're going to start seeing where the jet interacts with the ambient medium and drills the hole through. So numerical simulations now have become mature enough that we can span the gap in distances from the black hole all the way to the galaxy. And that makes it really exciting because we can start comparing the simulations to observations 1 to 1. So let me give you an example. First of all, what do we see here? We see that black hole plus a disk does produce jets. OK, by that mechanism, by the winding of the magnetic field lines. What else do we see here? Well, let me show you some more quantitative plots. For instance, here I'm going to show you the same picture as we saw before, jet radius along the vertical axis. And here I'm showing you the distance away from the black hole on the jet, which goes from 1 gravitational radius to all the way to a million. And you can see that there is a bunch of points which are data. And there is this red line, which is a simulation. So such a simulation carried out in axisymmetry, because it's easier to get to large scales, reproduces not just the shape of the jet naturally, which is roughly a parabola, as I discussed. It also reproduces the Lorentz factor versus distance. So this broken power law, shown with blue curves, this is what is inferred for the Lorentz factor from observations. And you can see the red curve is what is inferred from the simulations. You can see that the jets are messy beasts. The Lorentz factor can oscillate widely. It can have slowdowns. It can have accelerations. But by and large, roughly the trends are clear. Our simulations are able to give us something that doesn't obviously look very different than the observations. So what we see here is that jets accelerate as they collimate. As the opening angle becomes smaller and smaller, and this is what we have here because parabola collimates, we see that the Lorentz factor reaches relativistic values. In both cases, simulation observation around 6. And not only is the terminal Lorentz factor seems to be in agreement with observations, also the slope is in agreement. This is so far an axisymmetric simulation, but Kaushik is now ready to run full 3D simulation. In fact, we already have these results. We just need to analyze them. And what's also really cool is that jets appear to efficiently convert their magnetic energy to kinetic energy. So those jets that fly far away from the black hole, they're no longer strongly magnetized. They have more kinetic energy than they have pointing flux. I'm happy to answer more detailed questions after the talk. So this is great. Jets accelerate. But how do we understand what sets their power? Well, for that, let me step back and look at the central object, which is the black hole in our case, with a theorist's eyes. This is my best attempt at drawing. You can see I'm not really good at it, but it kind of does its job. So the black hole here, shown with the black circle, blue lines are magnetic field lines, which are vertical. I'm not showing the toroidal field, which will actually be the dominant one. And here, importantly, in the red, I show the meat of the disk in the vertical slice through the rotational axis of the black hole and the disk. So what will be the power carried by these jets that are produced by the winding of these field lines? Well, we can almost immediately write it based on dimensional analysis. The power will be, let me cover the spin of the black hole squared, will be the magnetic energy density times the cross section times the speed, right? That's the amount of flux through a pipe, right? So b squared over 4 pi is the magnetic enthalpy that's flowing out through the black hole cross-section, roughly r squared of the black hole. And everything is moving at near the speed of light near the black hole. So we've immediately written out the power, Blandford-Znaic power, that they analytically obtained in 1977. Plus, one twist here is, of course, the faster the black hole rotates, the more energy it has to dump into the jets, the more power we will get out. And it comes in a square because if we were to flip the sign of the spin, nothing would change in terms of power. Yes?
You just answered my question.
Cool. Thank you. Here we go. I read your mind. Great. So what can we do with that? I mean, there are a bunch of numbers. They're all free parameters. How can we make sense of this? Well, let's try and group them in the right way. Instead of focusing on the local quantity, the magnetic energy density, let us focus on the number of field lines. Because, see, there are 5 field lines through the jet, and that's a number that will be constant. So you can measure it at a large distance, for instance. So going to magnetic flux, which is the number of magnetic field lines threading the black hole event horizon, which I denote here with the letter phi. Given here, it's b times the cross-section. It will be a constant, so it's nice to switch to it. And what do we get? We get the power of the jet is magnetic flux through the jet times something that I will denote through the number k. That depends only on the black hole spin and black hole mass or radius. The two are proportional to each other, connected like this. So what that means is that if you picked your favorite supermassive black hole, its mass or spin don't change over the observational period. Therefore, k will be a number, fixed, for all our lifetimes. But yet we see a lot of variability in jet power in any given system on our human timescales. So that means that all of the variability has to come from the magnetic flux changes on the black hole. Yes?
Can't the spin of a black hole change during that?
But not during a lifetime. The time scale for a black hole spin change is comparable to the time it takes for the black hole to double its mass. So it's a long time scale, tens of millions of years, if not hundreds of millions of years.
Or we're talking about supermassive.
Supermassive black hole. For a core collapse, it's different. But I wanted to make it a little bit more dramatic to make sure that the audience is alive. So for supermassive black holes, this k will be constant. When it's not a supermassive black hole, when you're building up a black hole as a merger of 2 neutron stars, or when the core collapses, then over the seconds to hundreds of seconds, you're building up the black hole. It's growing in mass. So both spin and mass will change. And so this will be time-varying quantity. However, over periods short compared to the changes, the time scale for changes for spin and mass, you can still use this equation. It's roughly quasi-steady state on those small time scales. But on big black hole, for big black holes, this is a constant to really good accuracy over human time scale or simulation time scale, which is usually shorter than human time scale. So what is the range of this? Why am I asking you all this? We want to get some very basic understanding of jet power. So if we look at this, the obvious minimum number is, it cannot be negative because this is positive number. This is also a non-negative number. So the smallest number it can be is 0 when there are no large-scale magnetic fields, right? So this is a floor to jet power. But that's not interesting. What's interesting is what's the maximum energy budget of the jet and what is it set by? Not surprisingly, it's set by the accretion power. It's very hard for a black hole to produce an outflow that outshines the amount of food that you give to the black hole, right? Or else where will the power come from, right? So energy conservation. We feed it m dot c squared ergs per second. We get out p jet ergs per second. At the most, as much as we fed. So when we approach in this upper limit to jet power, and I'll explain why and what sets this value, the magnetic flux is as strong as possible. In fact, this limit is set by the maximum weight that the disk can have to hold this magnetic bomb that we have at the center. Because what we have here is a lot of energy in one place. This energy pushes out with some force associated with the magnetic field strength. Basically, magnetic pressure is pushing out, gravity of the disk is pushing in, and if magnetic pressure is much larger than the weight of the disk, it will just take it apart. So this is why there is a relationship between the flux and the disk density or mass accretion rate, and that's why there is a relationship between jet power and mass accretion rate. Yes?
Does it matter if you see the Eddington luminosity?
No, not for the jets. Here, I don't take into account radiation pressure at all. You can think of this as analog of Eddington luminosity. It's kind of Mageddington luminosity, magnetic analog of that. If the pressure of the magnetic field is higher than the weight of the disk. So outward pressure exceeds inward pull of gravity. That's the upper limit of what you can have for magnetic field on the black hole. So within this limit, magnetic field is dynamically important. It can do things it can do whatever it wants. It can push the disk around. And so this state is named magnetically arrested disk. I will show you the first simulation of that state in general relativity. Before I do so, note that if we divide jet power by accretion power, we will get a dimensionless number that I will call small p with the index j. And I will show you that, in fact, it can exceed 1 a little bit, maybe by a good fraction. So let's take a look at how it works. So that's a simulation. That's a black hole. Its spin is pointing up. So the black hole rotates this way, actually that way, counterclockwise. So if we look from above, both the black hole and the disk rotate counterclockwise. Color shows density. Red is high, blue is low. And this is 100 times 100 gravitational radii window on the life of the black hole. The simulation box extends out to 100,000 gravitational radii. So everything that you're going to see here will never reach the outer boundary. These three panels show accretion power here, magnetic flux on the black hole, and jet power. Both of these are normalized. So when you see that the jet power exceeds 100%, which is this dotted line, it means that we're making energy for free. So let's run the simulation and see what happens. So at first you see that the radial field lines got wound up and became mostly toroidal. The field lines here, they became wiggly. That's a telltale sign of a magnetorotational instability, which couples different distances in the disk and creates effective viscosity, which takes angular momentum out and brings gas inwards. You see there are blue funnels, which are filled with magnetic field that prevents the gas from falling in, and so does the centrifugal barrier as well. These are these relativistic jets. The density is very low. It means that they have a lot of energy per unit mass, a lot of magnetic energy per unit mass, and that's what allows them to accelerate to large Lorentz factors asymptotically as they convert magnetic energy to kinetic energy. And you can see here that while I was talking, magnetic flux in the black hole built up because it got collected from a large area. And eventually, now, it starts decreasing. How can this be possible? It's because the field became so strong, it pushed the disk aside and left the black hole. The gas is no longer capable of keeping all the magnetic flux on the black hole. Black hole is saturated. And so this is the state of saturation of the black hole with magnetic flux, or magnetically arrested disk, or MAD. And you can time average over these oscillations when the black hole binges on food, like I just binged on mother's dumplings. OK, well, bad analogy. So, and then the black hole loses magnetic field. And over time, you can take the time average. So I guess in the end, it will be my time average weight. And you will see that that's a well-defined number. Here, we can do the same thing with the jet power. And you can see jet power is a square of magnetic flux like we saw before. And the time average is greater than 100%. In fact, it's about 150%. So 50% of energy is coming out of nowhere. Well, it actually is coming from the rotational energy of the black hole. That's how black holes can lose most of their energy and inflate those huge bubbles that we saw initially. It's all coming from the black hole spin energy. This process is extremely efficient. You give the black hole about 10% of its own mass, and it will lose more than half of its rotational energy. So you need to feed it very little in order to extract most of the rotational energy.
What are these oscillations? Are they related by any chance to the Keplerian time of the ISCO?
This timescale is longer than the Keplerian timescale on the ISCO. It's actually quite a bit longer. And what I think this timescale is related to is, look, black hole just lost a lot of magnetic field. So it happens on dynamical time, essentially, light crossing time. It's a very sharp drop. And then it slowly builds up. This is the time scale for the disk just to realize, oh, there is now room on the black hole, so I can bring this gas with magnetic fields in because the black hole will accept that gas with magnetic fields. And so this is accretion time from the distance out to which the disk contains magnetic flux comparable to that on the black hole. So that's really comparable to accretion time, this time scale between the subsequent the time it takes for the flux to restore back.
How does it relate to the accretion time from your outer computational boundary?
It's much shorter. The outer boundary is at 10 to the 5. The disk is huge also. It's about 10 to the 5. So right now what we have is turbulence has established itself to be steady state roughly out to maybe 30 to 40 gravitational radii. So this still only rotated a couple of times. It's not yet in steady state. But as we run the simulation for longer and longer, then more and more of the disk will become turbulent, reach steady state. It will take enough time for the gas to fall into the black hole once, and that is what I would call steady state solution. So here it's around here, around 40. That's why I don't show much further distances.
So right now the black hole is rotating faster than its equilibrium range.
Exactly.
What would the equilibrium range be?
For this thickness of the disk, it turns out it depends on the thickness of the disk. Thickness of the disk here is 0.3, so 3/10. The equilibrium spin is 0.07. For practical reasons, what this means is black hole spin is 0, essentially, because 0.07 is essentially 0, which is spectacular because you feed the black hole, you feed angular momentum, but most of it comes out in the jet. So that's why the black hole slows down. When I first got that result, I was like, oh, that must be wrong. There's no way. And so, but that it works out. Happy to talk more about this.
So what is the accretion rate here? What fraction, if you turn it into light, what fraction of the energy?
Here, it's infinity. Sorry, 0. Because I don't have any radiation.
No, I'm saying if you turn the energy accretion rate into the velocity.
It's scale free. So I can double the black hole mass. Sorry, I can double. Yeah, if I increase the black hole mass or decrease it, all it does, it scales the length scale. It doesn't really change relative jet power or accretion power. It scales all of them. So if I were to double the mass accretion, if I were to double the black hole mass, the physical units of jet power and accretion power would go up by a factor of 2. So I can scale the system to any accretion rate I want and to any system size I want.
So I'm trying to get back at this question I asked you earlier. Most quasars don't have these powerful jets. And I'm wondering if it's just because, as you say, the equilibrium spin rate is low, and therefore you wouldn't expect to have much.
That could be a really attractive possibility, and that could be true. My suspicion is that quasars are transient events, comparable to transient ejections from black hole binaries.
But they accrete a very fraction of their mass during those events. Because we think they're on for like 10 to the 7 years.
Yeah. So we only see 1 out of 10 quasars producing a jet. So my suggestion is that 10% of that state where they create an appreciable fraction of their mass, they produce a jet. And then magnetic flux that produced the jet leaks out. When the quasar is in a luminous state, the power of the jet is less than this. So that jet wouldn't be able to slow down the black hole down to 0. So if I were to try and apply this model directly to an accreting black hole, I would say it works in super Eddington systems where it's non-radiative. Most of the radiation goes in or locked with the flow, and then this will work beautifully. Or this will work for really low mass accretion rates, but then you will have to wait forever until the black hole mass increases. So I might be actually able to answer your question a little bit later in the talk once I get to thin disks. Any other questions at this state? And I only have 10 minutes. Great. So let me see what I can do here. Do I have? OK. OK, good. Then I will be able to say everything that I wanted. So now, that was great. That was a big black hole. But why are you talking to me why are you talking to me about a big black hole? I will try not to rush. Because the most exciting thing is happening with small black holes. Black holes detected. Malevich predicted in 1915, 1 year before gravitational waves were predicted by Einstein. Please notice this. So as I said at the beginning, for those who didn't come here at first, I argue that this was the first prediction of gravitational waves. There are other exciting discoveries, like binary neutron star mergers. And these are small, 1.4 maybe plus 1.4 solar masses gives you a 3 solar mass black hole. So these are not supermassive black holes. So here we didn't see anything. Here we saw fireworks. Let me guide you through the fireworks that we saw. This is an artist's depiction, by the way. We didn't really see that. Okay? I took it from pngmart.com. So what happens when we take 2 neutron stars and let them merge? Well, at time equals 0, we get gravitational waves. And 0 is because I just started my timer then. Then, at least for the event GW17 or 817, about 2 seconds later, we got a gamma ray burst, a flash in gamma rays that lasted about 2 seconds. So that means that the central engine probably was active for those 2 seconds. That tells us something important about the timescales involved. Later on, oh yeah, and so one other thing I wanted to say is that later on we figured out from both the gravitational wave signal and from other ways that I will explain in a second, we figured that we were not looking straight down the jet, as usual for gamma ray bursts, because most of the jet emission that usually is a telltale sign of a merger comes along the jet because it's relativistically beamed. Here we were somewhere between 20 and 30 degrees away from the jet direction. So the fact that we saw gamma ray bursts was unexpected. Nobody expected this laser beam to ever point at us, and in fact it didn't. Something else must have produced, maybe the slow outflow that you were asking me that confines the jet. What was expected to be the signature of the systems when we looked at them off-axis was this, the kilonova. What is that? Well, you merge two neutron stars, two balls of neutrons. If you have many neutrons in one place, that is a recipe for disaster because you get a mushroom cloud that expands. And this is the mushroom cloud. But they were expected to be, perhaps two mushroom clouds. One is that one that doesn't have many neutrons, and the other one that has a lot of neutrons. In fact, people didn't know, shall we see both of them or only one of them? If you have very few neutrons, then you don't produce heavy nuclei that have a lot of absorption lines, and so the mushroom cloud becomes transparent to us early on and releases all of its light early on. That's why it happens on this timescale of 1 day. Whereas if you produce a lot of neutrons, you produce lanthanides, these F-shell bearing atoms. They have a forest of lines, so the photons get trapped for a long time, and so you have to wait for a week for it to peak or so. So we expected one or two. It turns out we saw both of them. What it means is that we don't have homogeneous composition. It's not one mushroom cloud. Literally, we have two different mushroom clouds, so we have composition variation across the mushroom cloud to have both of these components at the same time. Finally, this was not the only thing. Actually, we already have 1, 2, 3. We have a fourth thing, which is when the jet drove a shock into the ambient medium. The accelerated particles at the shock, the emission peaked on timescale of a fraction of a year. So we have so many different observables, so many different ways of looking at the system across the electromagnetic spectrum that this presents us with a unique possibility to try and test our models of accretion and injection. So what do we need in order to create a first principles model that will incorporate all of these timescales? I mean, that's crazy. From 1 second to a year, that is already 10 million in ratio, so 7 orders of magnitude, plus the time scale for the gas to go around the newly born black hole is maybe a few microseconds. So you actually are going from 10 to the minus 6 second to 10 to the 7 seconds. That is 13 orders of magnitude. So that makes this problem extremely, extremely hard. So what do we need to do in order to make a baby step in understanding it? We need to understand all 4, though. So the minimum requirement is we need to run a simulation of the central engine for at least twice as long as it was active through the prompt emission. So maybe 2 seconds. But 2 seconds, it's about 1 million dynamical times near the black hole because, yeah.
It's not clear that if you observe something for 4 seconds and the engine was active, it could be that the engine was active for shorter, it's just a beaming effect, right? It's a relativistic effect.
It's very hard to create new variability. Because relativistic effects, they usually cancel. Because you started something that wasn't relativistic. It became relativistic. And so whatever variability you feed at the bottom, unless you have complicated radiation transfer effects, you will see this variability come out at the top. We can talk about this more offline. But I will show you, actually, that you can naturally get variability from the systems that last even longer than 4 seconds. Which is really surprising because mass accretion rate, almost all the gas gets eaten in a fraction of a second. So how can you get something that lasts that long? That's a mystery. And I will give you one potential answer. But ideally, we would like to explore this, and we would like to run the simulation for at least 4 seconds. And the other thing is, if we want to get a jet, we probably want to include a lot of vertical field. Remember, vertical field is what we need to feed the black hole to produce the jets. And also, we would like to have a big disk. Remember, there was a big disk, and it produced the collimating jet. If the disk was small, there would be nothing to hold the jet together. It would just fan out. Because the jet was collimated here, we want to have a big disk. There's only one problem, actually many problems. 4 seconds is about 250,000 of dynamical times. This would be the longest general relativistic simulation ever. very expensive. And if we want to run a few of those, that would be crazy. Post-merger geometry, or rather the shear in the post-merger disk, prefers toroidal fields because it amplifies it during the merger and after in that direction. So it's not clear whether they will get any jets at all from the toroidal field. And finally, post-merger disks are small. They're like 10 gravitational radii in size. So we will not get any jets at all, maybe, that are collimated. So we are deeply in trouble. But let's be brave. Let's try it out. And we will try it out. We will try to play out different scenarios. Scenario number 1, where we start with a black hole of 3 solar masses, actually in both cases. So the result of a merger of 2 1.5 solar mass neutron stars. We will start with a disk that's in about 10 gravitational radii in size. And we will put some poloidal field in, this loop in the plane, in the vertical plane. So this, hopefully, because there is poloidal field, will produce a strong jet. But because the disk is small, we expect no jet collimation. So that shouldn't probably work. We chose it such that we could resolve the magneto-rotational stability. And then we reran the simulation for 3 times as weak field, where we put all of the power of the computer that we had because it required us to put higher resolution. And I have answers for both. So we get trends. And then in reality, the poloidal field should be much weaker than what we could afford computationally. And then all we can do is either get a bigger computer, which is what we're in the process of doing, or extrapolate. So I will do both. And here, you see that there are no field lines. What does it mean? We cannot start with purely hydrodynamic simulation. There will be no viscosity. Yeah. Here, the spin of the black hole is 0.8. It's a typical outcome from a merger of 2 neutron stars. Orbital momentum neutron stars gives you the spin of the black hole. So it's pretty much fixed. Great question. Here, the field is purely toroidal. Here, we don't expect any jet at all because toroidal field is known not to produce any jets, because you need this to produce jets, and no jet collimation either. So let's see if I get proven wrong. Oh, by the way, so this is published in Rodrigo Fernandez, myself and others this year, and then also Ian Christie, a postdoc working with me, and a graduate student, Aris Lalakos, are working on the follow-up, this part. So let's flip our fingers and run the simulation. At first, things are going slowly, but then we will accelerate the movie because otherwise we'll have to stay here for the next month. That's a very long simulation. So you can see that in both cases, the flow does something. I will pause it here. You see here, because we had vertical magnetic fields, they launched strong bipolar outflows. And what's really exciting is that even though we started with a tiny disk, here the disk has expanded due to the viscosity provided by magnetic fields and became much larger, almost 100 times larger. And that allowed to collimate these jets. So we can get collimated jets even from small disks because they will expand over time. On the other hand here, it seems like our prediction of no jets holds. There is nothing that came out of here. There is something that is not really a jet. But let me now freeze the zoom out here, and I will let the system play out in front of us. Right now, we are just at 20 milliseconds. It's very early on. Let's run it all the way up to 5 seconds. It took us about a year to get there of simulation time. So you see something happened here. The jets got formed, and you see they are intermittent. The jet sometimes switches on, sometimes switches off. But in both cases, we see that they are very well collimated, more collimated than 10 degrees, small opening angle at 10 degrees, which is consistent with observations. The disk has become huge, spanning many orders of magnitude in distance because of the viscous spreading. And in fact, we ran the simulations, this one, almost all the way to 10 seconds. So what do we learn from here? First of all, we can measure the jet power, and they span from about 10 to the 49 ergs per second to 10 to the 51. So you can see we span a wide range of jet powers, which is actually less than what's observed. Even weaker jets are observed observationally. Yes?
So what's driving the viscosity on the right-hand side?
It turns out that in addition to vertical MRI, there is also toroidal MRI. And this toroidal MRI, it can convert, it turns out, toroidal field into vertical field due to a process called large-scale poloidal flux dynamo. And that turns out to be the first demonstration of this dynamo in the small disk. So it just worked out. Great question. Any other questions so far?
What time scale is most the energy released over?
Give me 1 second. I will give you that answer. Both poloidal and toroidal fields, vertical and horizontal, can produce jets, which is really great because it means that there is no fine-tuning. No matter what you put in, you will always get a jet out. But sometimes you can get stripes when you start with the toroidal jet, which is amazing because stripes is what many of us have been looking for, and now we get them for free because the system doesn't have a preference for up or down magnetic field geometry. And so when this magnetic field geometry gets sheared out, you get toroidal fields in opposite directions. They can reconnect, produce gamma rays. So that could be a way to dissipate energy in the jet self-consistently without imposing it, which is really, really cool. Jets collimate and accelerate off of the disk that has now become much bigger due to viscous spreading than before, which solves our collimation acceleration problem. And finally, we need mass ejected in the mushroom bubble. And here, as much as 40% of the mass gets ejected, and there 25% of the mass. So the magnetic field geometry does substantially affect the ejection of the mass, and therefore the brightness of the kilonova bumps that we're going to see. But it's all within a factor of 2. So in both cases, we're going to get the kilonova. Now, coming to your question, Chris, what sets the duration of the radiation? And so here is my cartoon. This is actually at first done for core collapse gamma ray burst. I stole the slide from myself back 4 years ago. And so what I showed then, and I said that initially mass accretion rate starts at a big number. This is time, and this is jet power. It starts at around a fraction of a solar mass a second, and it drops down in time over a time scale of a collapse of the star, which is 100 seconds. The jet power, however, stays roughly constant initially, and because, remember, it cannot go over mass accretion rate or accretion power, it has to follow it. So here, the value of jet power is determined by the amount of magnetic flux. Remember, K times phi squared? That's the luminosity of the jet. And here, it's determined by the mass accretion rate because it's in a mad state. You cannot jump above the feeding energy. So that is a natural light curve that you expect from any system where mass accretion rate drops, magnetic flux stays the same. So even if initially magnetic flux was not important dynamically, because mass went away, this flux eventually is the winner. And so this is the point where it wins. This is the point where it turns mad, and then it follows mass accretion rate. So in a short JRB, the same thing holds, except maybe the level of power changes and the duration of the prompt emission changes. So here we get it to be about 1 second. So what if we take the ratio of red to blue line? Then we're going to get this. We're going to get something that was small, because red was much less than blue, and then it increases all the way to 1, because here they're comparable to each other. That's what we expect theoretically. So let's take a look at what happens in a simulation. Ooh, sorry, somehow this thing is too sensitive. Or maybe I drank too much coffee. So here are 3 simulations that we carried out. They're color-coded. So this one is red. The red one is strong vertical magnetic field. This green one is weak magnetic field that's also vertical. And this one, the blue one, is no vertical magnetic field. That's the toroidal magnetic field. The axes are the same. This is the ratio of jet to accretion power. And the time scale here is 1 second. And that's 10 seconds. So you can see that almost all of these simulations eventually approach, like we expected here, order unity ratio. And you can see the stronger the field, the stronger the vertical field we start with, the earlier it reached unity.
The short JRBs typically are much less than a second.
So you can see that we can get a jet that lasts a fraction of a second. You can see that you can get a jet that lasts much longer than a second. And you can have a jet that has a spike initially, which is much shorter than a second. And all of this is much weaker because here I normalized jet power by mass accretion rate. So what you will probably see is just this one blip at the beginning. So we can have a full range of variability in time scale. And if we had a very, very sensitive telescope, we could see time variability at late time. That might be happening on time scales of a few seconds.
But didn't you say the jet happened after a second after? So 1 second is much.
There was a delay.
So this is not delay. This is maximum.
It's not shown here. Yeah. Here I start my time at -1 second, and this is at 0 seconds. It's because you see emission not from the jet itself. You see emission, we think, from the surrounding material, which was moving slower than the light speed. And so in order for the outflow to release its photons to us, it needs to propagate far enough for it to become dilute enough for the photons to be able to see us, and us see the photons. So it needs to become optically thin. And that takes a while. And because the flow is not moving at the speed of light, it's moving slower than the speed of light, gravitational waves have already outrun the outflow. And only then, somewhat time later, 1.5 seconds later, will the photons be released. That's why there is a delay, we think, between when we detect the photons and when we detect gravitational waves. It's because what emits is not the center itself. It's an outflow that propagates slower than the speed of light. So the photons, so the gravitational waves outrun the emitter.
What is the physical value of the magnetic field in your intermediate case?
In the disk initially, it's pretty strong. It's about 10 to the 14 Gauss. It's still stronger than you expect.
So that in the neutron star, that would be even stronger, like 10 to 15 then, because you spread it out within the disk.
So there is a question of what happens in the disk. Does it get amplified through through turbulence? We don't know. So we put it initially by hand just because we couldn't do anything weaker than this. And yeah.
But of course, it's an interesting question whether some of these binary systems could be a neutron star magnetite binary. I mean, we don't know.
Let me ask an important question. How many more minutes do I have before you all get up and go?
5 minutes.
OK, so let me show you a completely different part of the talk. Before I do so, I will just show you why you should invite Ian to come and give a talk here. You can also measure what is the composition of the outflow. There will be a jet, there will be blue component, and the red component. And so that all comes out from the simulation, so you can convert it into light curves, something that we are working on. And that's all I'm going to say. We haven't done them yet. We need to. Sorry? Neutrino can affect that. And that's something that we want to improve on because we don't have radiation transfer, we don't have neutrino absorption, so there could be even more blue than what we show here, if that's what your question about.
Yeah, I just wonder how you can even know that anything is blue without neutrino observations. Yeah,
so we do include basic weak processes that are responsible for neutrino emission. We do not include neutrino absorption. So that is included, but we're working on that. The other thing that you can do, you can also ask what happens to the afterglow. And that's a work of graduate student Adithan Kathargamaraju, who is now going to Berkeley as a postdoc. And what you can see here is that there is the solid line, which is the simulated afterglow emission light curve. And it goes right through the points. And what's spectacular is that there is just one free parameter here. The one free parameter that we don't understand the physics of is the efficiency of acceleration of electrons. That's it, nothing else. And by varying this one parameter, we can fit the shape of this flow, which is spectacular because the distribution of energies, the angular distribution of energies, which is usually prescribed, is actually fixed here once and for all. So this shows that these simulations actually are pretty close to what we observe. At least it passes the test of the afterglow. So what I wanted to finish off, and this will take me a couple of minutes to go through, is what I started with. We start with something that looks completely disfigured. It doesn't look like accretion here and ejection over there. What it looks more like, it's coming from some random direction. So why are we all simulating accretion here, ejection straight out? Well, we should be doing this. And which way will the jet point? I will not know until I run the simulation. So when the disk is thick and tilted, the standard theory says the disk will precess like this. When the disk is thin and tilted, and these are interesting because if they're thin, it means that they're cooled by radiation. They are really bright. Here we expect the inner parts to align with the black hole. And I will not go into the details why, but this was predicted in 1975, and it has never been seen in a general relativistic or even in any simulation where the disk was magnetized and turbulent. So the question is, do thin disks ever align with black holes? It's really important to understand how black hole spins evolve. And why this has never been done is because the cost to simulate the system is very, very expensive. Because if we take a disk of height h and distance r, the cost to simulate the system goes as h over r to the -5th power. So if you want to study this that's twice as thin, you have to pay a factor of 32 in computational power. So that's why it's difficult. So how do you solve a difficult problem? I already showed you my method. I find a bright graduate student, Matthew, who converted the code that I used to simulate these things before on GPUs. So from CPUs, we go to GPUs. Why GPUs are great? Because there are many more gamers than scientists. GPUs are much cheaper per computational unit. And so for 3K US dollars, you can get a GPU that gives you 100 million zones per second. With CPUs, if I were to combine all the CPUs I needed to get that speed, I would have to pay 10 times more. Then he implemented adaptive mesh refinement, adaptive time refinement. That allowed us to get a lot of computational time on supercomputing resources. The bottom line is we're no longer limited by computational resources. We can do anything. We can run any simulation we want, essentially. Of course, there are limits, but nothing to worry about. So let me show you the big result that we got. What will happen if we start with a disk that is tilted relative to the black hole, so black hole spin is up. This is a zoom in of the central region here. Blue is low density, white is very low density. The tilt initially is 45 degrees, and the thickness of the disk is 0.03. This is twice as thin than the thinnest disk ever simulated. And this is also tilted. So it's crazy. This was done on Blue Water supercomputer. Let's run the simulation and see what happens. And the simulation doesn't run. I know why. So first, the disk cools to our target thickness. Then you see there is a sign of alignment here with the black hole, but then it goes away. So we got really disappointed. That's what we were looking for. We're going to thinner and thinner disks, and it's not there. But there are interesting things. Like you see these jets, which are produced by these really thin disks, which we didn't expect. And these could be trying to answer your question that even thin disks can produce jets. And wait, there is something going on here. Isn't that an aligned disk? That's an aligned disk. So maybe we've solved the 44-year-old problem of whether such disks align. But not only that, these disks align and also break off from the outer disk, because a disk cannot just smoothly bend over like this. It develops a sharp break. And this is really cool. Let's zoom in. So this is a disk that's tilted, and that's the central part that's aligned, and there is a break over here and there. Let's not stop here. Let's go to a disk that is twice as thin. And what you see is that the alignment radius increases. So in realistic systems that are closer to this than to the previous slide, we can have substantial distances over the disk will be aligned. What's even more spectacular, perhaps, is what if we tilt this disk by 65 degrees instead of 45? What's going on here? In 3D, this is what it looks like. The outer disk developed an inner disk that just broke off of it. Why is that? Because black hole tries to cause everything to precess that's tilted relative to it. So the disk wants to precess, but the precession speed becomes faster closer to the black hole. So the inner disk just says, I'm not going to wait for you, outer slow disk. I'm going to precess at my own rate. And so that's why it breaks off. You can see this in the movie. That's initially tilted disk, and that is a jet perpendicular to it. And you can see that there is one disk already broke off of it. And then that one will break up into subdisks several more times until the final disk is so small that it can't break anymore. And that one will be aligned with the black hole. You can see jets can destroy the outer disks. It's about 20%. These jets can destroy disks. Disks that are precessing can obscure the central source. And sometimes absorbers fly in front of black holes. Maybe it's the disk itself that's flying. You can see that there is a lot of dissipation between different disks. They can go in opposite directions, and crazy things can happen. Jets can run into disks and create a lot of non-thermal particles. All of this is probably happening in real systems. So we need to understand what's happening. Now see, the disks will merge together, and then they will try to tear apart again in the same place. And at first, it kind of tries to resist, and then eventually it breaks off. So there is a lot of exciting dynamics that we're just starting to understand. And in fact, what we're trying to do now is to try to understand what are the observational signatures of this breaking. This is a real thing. It was predicted in Hydra models, but now we see it in full 3D turbulence simulations. So we need to pay attention. The time scale of this is around tens of thousands of light crossing times of the black hole. So the bigger the black hole, the slower these time scales will be.
So this is gravitational radii, it's the vertical axis.
Yeah, so it's about 200 gravitational radii. But this is just because we start with the disk this big. Because if you start with a bigger disk, you have to put grid cells over there. So we started with a relatively small one. But if the disk is even bigger, then the outer disk will not precess at all, and it will be easier for inner disk to break off. So it's possible that this break-in would have started even earlier. Now I've exhausted you. I'm going to finish. We've now shown that with the numerical simulations from first principles where we resolve the turbulence, we can simulate electromagnetic counterparts to gravitational wave events that last for seconds, which means that we can simulate the jet lifetime over the entire lifetime, jets over the entire lifetime that they observed. Both vertical fields and toroidal fields can produce jets. That means jets are really robust. No matter what you do, no matter what you throw at the black hole, a jet will come out. We're just starting to understand the completely new freedom of tilting the disk relative to the black hole, and we're getting pretty amazing results. Not only do we get alignment that has been sought after for the past 44 years, we're also finding that disks can break up into individual subdisks and create all sorts of interesting spectral and time variability signatures. Thank you very much. That's all I have.
So maybe just one question, because we're running our schedule as it is. So
Well, I say just beautiful, this last exercise.
Thank you.
It's all beautiful. Yeah. But back to the initial question I asked. The most remarkable thing about these double load radio sources like this thin jet, nothing is coming off the side. And in your funnel simulations, you're not showing the entire structure further out than what you showed us, but there is stuff coming off the side. And so why doesn't one see that?
Thank you for setting me up. I have an excuse to show you one slide because you already saw this one. So this one is stable, this one is falling apart. Why? What's different about this? This is another 40, sorry. How many? You can tell me, 45-year-old problem, right? So this one falls apart, that one stays constant, straight. So in hydro, that's what you get. You take a hose, garden hose, send it against the wall, it bounces back. Water goes out, bounces back at the hot spot, that's the backflow. Here, the thing has already fallen apart. There is no more garden hose. It's already fallen apart. That's why it's, and here the exhaust comes back. Here the exhaust outruns the jet. Something bad is happening to this jet. So what people tried to do to reproduce this, they stuck stars into there so that they would mass load with their wings and the jet will fall apart. But I started thinking, when I was a kid, I would take this, pens, right, with the springs inside. I would take them apart, and I would squeeze them. And when you squeeze a spring, what happens to it? It doesn't stay like this. It's unstable. It will fly sideways. That is a magnetic kink instability. So this guy is 70 kiloparsecs long. The galaxy is tiny. This one is only, this galaxy is only 5 kiloparsecs long. The galaxy, most of the gas is here. So this guy is heating up the galaxy. What makes it fall apart in this distance? Well, maybe it's the magnetic.
Eddington accretion region?
So all of these are sub-Eddington. The interesting length scale here is the Bondi radius, which is a fraction of a kiloparsec. So this is outside of the sphere of influence of the black hole. So let me show. This is the slide that I promised. This is 10 kiloparsec circle for the case when the jet is powerful and less powerful. This is Cygnus A-like, and this is M87-like. The only difference between this and that simulation, apart from the zoom, is that this jet is 100 times more powerful. Ambient medium is the same. So let's run the simulation and see what happens. Here, this one single field line I trace out just to show you what happens to the jet. And you can see, so let's focus on this one first. There will not be much happening here. So you can see what the jet is like. It's a magnetic spring, or you can think about it as a bendable drill. So we tried to put that drill into the wall, and if the drill is strong enough, it will kind of wobble around but make a hole. You can see it makes a hole, it makes an exhaust turns around and flows back, just like this jet. It makes it all the way to the edge of the galaxy, and then the density drops off faster. It accelerates and deposits energy into the IGM. Victory. And you see there are bends here on large scales comparable to bends over here. You see, if you look from the side, you will see the jets are showing bends.
Are you injecting the jet here, or are you putting
At the Bondi radius. So I put a big sphere with magnetic field sticking out, and I twist it by rotation. I do not send it off. And this is a key point that allows me to get the right magnetic pitch angle, which I will not get into the detail. Otherwise, I would have a free parameter of how strongly toroidal dominated the jet is. Here, this jet is still struggling to get out. You see it's twisting itself into knots, falling apart, and inflating this kind of yellowish bubble. Much like here, you know, there are pieces of jets that are falling apart. It can't propagate. That's because it's unstable. It turns out that the radius of where the jet becomes unstable is proportional to its power. So if the power is 100 times less, if it's less than a critical power for the jet to reach the edge, it will never make it out. It will stick there forever and will be struggling to make out just like this one. And by the way, this is 5 kiloparsecs, this is 5 kiloparsecs, and I didn't tune it. It just happened like that. Does it answer your question?
I'll ask you that.
OK.
So we're out of time, so let's thank Sasha again.